colleagues Matthew Cohen, Stephen Tamburo, and Matthew Constant. We've been working with Hayward Industries to improve their current model of their chlorine generator cell tester. So to start out, a little bit about Hayward. Hayward offers environmentally responsible, cutting-edge pool and spa equipment for both residential and commercial in-ground and above-ground pools. And more specifically, we will be working with their chlorine generator. Now, for those of you who don't know what a chlorine generator is, basically, the cell uses electrolysis to convert the salt water in the pool into chlorine automatically. This is more convenient than going to a pool store and manually adding chlorine to your pool every so often. Also, Hayward is the largest manufacturer in residential swimming pool equipment, and their electronic and software design center is located about 30 minutes from here in Quonset Point, Rhode Island. Project motivation and goals. So our motivation for this project is that Hayward spends over $300,000 annually in unneeded warranty claims. This is due to the fact that their old design was bulky, time-consuming, confusing, and requires instruction to use. So up here you can see this is their old design of their chlorine generator cell tester, and this right here is a chlorine generator cell. So our best anticipated outcome was to design a foolproof method to eliminate the $300,000 spent annually in unneeded warranty claims. We were going to do this by designing a hassle-free design for both customers and technicians, an intuitive user interface that clearly displays all essential test results, and an all-around fast, portable design that is user-friendly, easily replicated, and deployed. Unfortunately, we were not able to reach our best outcome. We were, however, able to complete our schematic as requested by Hayward and verify this by breadboarding our entire prototype. And we were able to order our PCB, and it came in with just enough time to populate it. However, we weren't able to complete all essential testing. Now I'm going to hand this over to Matt, who's going to talk about project design and validation.
So project design and validation. So even though we did not achieve our best outcome, we achieved a great deal this semester. So we were able to confirm a new testing method. We finalized our schematic and board layout as seen to the right. We utilized LT-SPICE simulation software for our sensing circuit. We populated the PCB in which we ordered. We designed a scheduler to execute tasks in software. So the beginning of the semester, we had left off where we had left off in the fall, in which we had a sensing circuit that could determine the resistance of a cell based off of the voltage and current of the cell. In the fall, it was able to differentiate between good and bad cells. So the first part this semester we wanted to was to test the accuracy of the sensing circuit. So in order to do so, we inserted known resistance values, so like a 10 ohm resistor, for example, so we would be able to determine how accurate our sensor was. Upon doing so, we found out that the percent error was slightly too high for Hayward's approval, so we needed to develop a new sensing circuit. In order to do so, we utilized LT-SPICE simulation to get better results. The modifications we made were many, but some major ones included separating the voltage stage and current stage. Before they were just one circuit, and with using a MUX, we were able to get the voltage and current separately. So this time around, we made them individual, and we had different gain stages in the differential amp stage. In doing so, we were able to improve upon our results, so we were able to then create our sensing circuit.
All right, so in designing our new improved testing circuit, we had to make sure that it would be able to properly read the cells, because essentially it is act like a big resistor. The older or worn out the cell gets, the higher its internal resistance. So to do so, we tested a few cells to see how they behave. On the left there, you can see our good cells, and they have a high current and thus a low internal resistance, which is what you want. On the right there are bad cells, and those have nearly no current flow, and thus no chlorine is getting generated, which is obviously bad. Additionally, we found that water with a higher salinity, thus a saltier pool, will result in a lower overall impedance. So that means a bad cell might actually appear good to the tester, so we had to account for that in our final design. And here's what we came up with. We utilized a program called Pulsonics provided to us by Hayward to create our final schematic and board layout. This includes all aspects of the final tester, so sensing circuitry, user interface, connections for our MCU, as well as our power circuitry. floor here. Up top, we have our connectors for the T-cell, that's where you plug it in. Down here is our user interface, so our menu and select buttons, as well as our power on and off buttons, which are tied directly to our power supply. On the left here are our indicator LEDs. Now there's a green one, a yellow one, and a red one. And that corresponds to a good cell, a marginal cell, and a bad cell. Right here we have our LCD display, and up top we have our main circuitry. So that's all of our sensing circuitry and our drivers, as well as our power supply. And for our power supply, we decided to go with 4.5 volts, so 3 AA's for simplicity, so the pool technician can easily swap it out if it goes dry. And we also added regulators to step that 4.5 volts down to 3.3 volts, which is required by our MCU. And finally, right here, we have our connectors for the MCU. Now, we decided that it would be much simpler to simply stick our MCU and launchpad directly on the PCB rather than adding a dedicated socket, which would be more complicated, obviously. This will also aid in any debugging or reprogramming that you would have to do, since this is in fact just a prototype. And with that, I'm going to hand it off to Matt, who's going to talk about our software.
So in terms of software, last semester was focused primarily on writing the firmware to work with all the different components of our project, such as the UI components, the hardware that they all designed, and the peripherals available on board the MSP430 microcontroller. This semester, our focus was shifted towards using this firmware to write tasks that were required of us for this project. However, before we could do this, we needed a way to execute these tasks when needed. To do this, we used a simple scheduler, which could execute tasks based on time interval and the current state of the machine. Once this was implemented, we simply assigned a time interval, such as 5 milliseconds, and a state or states to each task, which could then execute these when needed. Now that we had an environment to run all of our tasks in, we then had to actually write these tasks. Since one of the main goals of this project is to provide a simple and intuitive user interface, we started with the UI task and the finite state machine task. These both run continuously regardless of state and provide the user with a very responsive and easy to use user interface. Once these were done, we then went on and broke up our previously created flowchart into many different tasks. In the end, we were able to develop tasks for most of our key aspects of our project, most importantly, the T-cell setup and testing. These two allow the user to define different options, such as the T-cell model being used, and then run the actual test, which determines if the cell is of good or bad health. And here we have a simple hardware block diagram showing the different components of our project. We have our UI, which comprises the character display and buttons, and then our custom hardware here, the test signal driver, sensing circuit, and power supply circuit, and finally our MSP430, which controls all these different peripherals. And lastly, we'd like to thank our technical directors, Jamie Murdoch and Joe Bindell, as well as our capstone director, Dr. Sunak, for all their hard work and dedication. Thank you.
Thank you.